Schools in Northern Ireland are required as part of the national curriculum for technology and design to teach computer-aided design and computer-aided manufacturing, processes used extensively in world industry. At present, the least expensive system without the computer will cost in the region of $15,000 American dollars, which is outside many school and college budgets. In addition, the systems are very difficult and complicated to understand and operate. In response to this, we decided to undertake a project on computer-aided manufacturing that is easier to use than current systems. The main aims of this project were to carry out research into computer-aided manufacturing and to design and produce a small-scale system that has the ability to take an image on paper and cut its three-dimensional form into a block of material. We researched heavily into the area and produced information on computer-aided manufacturing systems, current operating methods, power supply systems, programming techniques, positional control, and three-dimensional graphics routines. The milling machine, also known as Caisam, is very portable and can easily be moved around the workshop. The connections are located on the side of the machine to allow Caisam to be easily set up. The mill system will accept an 120 volt or 240 volt mains power supply connection. Connection is made through the parallel port at the back of the computer. The flexible mounting system allows different shapes of material to be held securely for cutting. Cutting is along three linear axes, X, Y and Z, and coolant is used to clear the work area from swarf and keep the mill bit cool. Materials can either be soft plastic or, in this case, wax. Cutting can also be carried out without coolant at slower speeds. Access to Caisam's internals is simple, requiring only the undoing of two screws. The coolant tray is neatly contained within a partition inside the mill and can easily be removed for refilling. A fine mesh filter mounted inside the tray removes all traces of swarf and waste from the coolant. To pump the coolant, we have used a simple windscreen wiper pump as shown on the right. In addition, a sensor to measure coolant level is included. Connecting and disconnecting of the coolant tray from the mill is simple, with only a tube and a deconnector to be removed. Refitting is the reverse of the removal procedure. The coolant pipe can be positioned for efficient coolant action. Coolant then drains back to the tray through the copper-lined tubes. The axis moves using an M14 2mm pitch stainless steel rod, which has been used to reduce corrosion. Brass sliders keep the axes on line. The stainless steel screw is driven by a 1.8 degree stepper motor. The stepper motor has 200 steps per revolution, which means each step will turn the axis 0.1 mm. The Z-axis uses exactly the same method to raise and lower the drill. The drill is a simple PCB drill, which has not been specially adapted. The speed of movement can be adjusted by increasing the delay between steps. The block can easily be removed after milling. Positional control is obtained using the magnetically operated reed switches, which are permanently sealed in PVC tubing and are located at the end stops of the axes. A reed switch is also used to detect the lid position for safety purposes. By removing the lid, you can see the contents of the casing. The system has been designed so that the lid sits flush with the case without protruding wires. The circuit board is a compact unit which has been designed to accommodate all necessary components. It is a single-sided board with minimal hard wiring. The power supply is divided into 5V, 6V and 12V supply sections and is cooled using a fan and several heat sinks. The water level sensors send information back to the circuit, which can then be interpreted by the computer. The 3 stepper motors are connected to an SAA1027 driver chip, which has power delivered to it by a 555 timer chip when pulsed by the computer. This is repeated for the Y and Z axes. The power to the stepper motors is amplified by a series of transistors to drive the stepper motors. We opted for a dual power supply with a toroidal transformer to provide the high currents required by the stepper motors. The power supply is encased within an earthed safety box. Due to the high current demand from the drill, power supply unit and stepper motors, relays have been used to switch the high currents. lid is removable and can be easily relocated. An emergency foot switch is provided, complete with indicator LED, to stop the system in the event of an accident. Software has been written for Microsoft Windows, complete with manual mill control, resizing the axes, and emergency stop provision. An image can be scanned and the points located for cutting. The RISC-OS software incorporates more features. The RISC-OS software features include profiling. Following this, you can either use set profiles or use your own. A program called Visualize is used to give a comprehensive three-dimensional view of the object to be cut. The object can be rotated and zoomed. An image can be dragged onto the scanning program, which will calculate the X, Y, and Z movements needed. The system will efficiently scan for different bit sizes. Points can be edited using the sequence editing program. Points can be inserted either as moves or cuts, and even at this level the system is significantly easier to use than ISO code. Other programs make up the complete software package, including a manual control program, a drawing program, an ISO code converter, an editor, a multilingual support program. A direct manufacturing program. An image processing program. An X, Y, and Z point reader. An image scaler. A sequence editor.